one of your employees comes and says, I'm upset, it's your turn to be the 20%. Okay, so this is what we got. Why am I dead? Okay, so on, this was the test, and so easy to difficult, and that was right down the middle, right? 50% of you thought it was easy versus fair, or easy versus difficult. Most of you did think it was fair, though. 80% thought it was fair. So this was the question about the course in general. So do you think that this material is too redundant or we're going too fast? And just, again, it was right down the middle. Slightly more of you thought we were going too fast, I guess. That was me. Am I clueless or am I an expert? And so I think I'm above 60%. So, but I call attention to the size of the error bars on this one. I think this was. More than 20% here. This was the homework. Is it helpful or is it not helpful? And that was kind of surprising. So I don't know what to do. So homework's like one of the things that we're going to talk about. This was chalk versus PowerPoint. I'm trying to continue to mix it up. There was no firm conclusions here. This was, would you recommend the class and would you recommend the instructor? So these were, I scanned through the comments and I looked for consistency. And so where did I start to see similar comments? And this was, I got this a couple times, that the homework should be optional and that it's available online but not for a grade. And then I saw this a couple times. The exam was fair but too long. And I can appreciate that. So I think we'll tone it down next time in terms of just the volume. But homework, then I don't know what to do because frankly, I would like to get rid of some grading too because I'm like killing my TAs to grade like, 70 times 8 problems a week. So last year what they did is the TA just picked at random which questions they were going to grade, right? That's one way to do it. The other way, is that like, do you see that in other classes? Is that that's a thing that happens? Oh, okay. What's that?
It's like Nano 101 was like that. Nano 108 was you had to turn it in. Right? Nano 101 was off the
Okay.
We also had homework, like classes where they will give you a whole homework assignment and then only like the first 3 questions are graded.
Do they tell you in advance which ones are graded?
Some do and some don't.
Some do and some don't. Okay. Maybe we'll do it. Yeah, I'll definitely do that. But I mean, I also wanted to use the grading as like a buffer to help pull the, So the other option is to just quit grading it, always post the answer key, and then make the exam worth 40%. No? Okay. I mean, we could, yeah. So grade fewer, but just more attention to detail on the grading. Okay.
If you did all of the homework, you get at least 50%, and then if you get 2 questions.
So then they're just going to scan through and be like, something's there, something's there.
You also check like 2 of the problems to see if it's right. So
Yeah.
it's not entirely dependent on the 2 problems.
Okay.
But like arbitrary numbers.
Okay.
I think just less questions, like 4 questions.
Fewer that's fine with me. These are hard to make up. Okay. Yeah, they are, man. Yeah.
I think like if you're like asking us to look stuff up online, like could you like put the constant there because like Google sometimes gives us like 5 different things.
That's a fair point. Yeah.
I think just like putting the away from the homework, or just not putting the homework and just putting like 7% on the 3 exams instead of putting it all in the final.
So that's an idea. Do we make no? You want to still keep that homework buffer? Okay, that got shot down. Sorry. I saw heads shaking in unison. Yeah.
Regardless of what different homeworks have already been weighted very differently. We had one that was 75 points. One
Yeah.
was 200.
Those will all be normalized. Yeah. Don't worry about that. Okay, so then maybe what I'm going to decide is that we'll knock this down to like 4 or 5 questions, and we'll grade 1 or 2 of those. And maybe since my goal is to make this a buffer, I'll tell you which one is going to be graded. Is that a consensus? Okay. So we need to all fly to Washington, D.C. and show them how it's done. Jesus Christ. Okay, so on to more density of state stuff. So when you search for density of states, if you do an image search, this is what comes up. This is the most popular image on all of the internet for density of states, and it looks nothing like what we talked about, okay? So why is that? So let's go back to what we were first talking about on our hydrogen. Okay, right, where this is energy. And let's just call this like an arbitrary 0. So if we were to look at maybe every 2 electron volts going up or down, right? So let's just say that this is 2 electron volts down, -2, -2, -2, right? So by here we're at -6. Okay. So if we were then to calculate the density of states, the number of states per amount of energy, which is what density of states defines, right? How many would be here? Like 1, right? 1 state per 2 eV. Now let's look here. Maybe we get 1, 2, 3. 3 states per EV, per 2 EV. And maybe here we've got, let's just say it's 10. Okay? So here our density of states then would be 0.5, 1.5, and 5. Same thing down here. Okay? So now then when you went to plot density of states, which is a very other common way of looking at this, as a function of energy, so now again, we're at 2, 4, 6, -2, -4, -6. Okay, so then, so from 0 to 5. So at 2, we have roughly 0.5. I'm sorry. And then at 4, we have 1.5. And then at 6, we have like 10. So that's why we see something like this. So when you start to look at other resources, this is why this is showing the same thing here that we showed here. Does that make sense? Because, and it's not like we're dividing this by 2 plus 2, or 2 plus 2 plus 2, we're the number of states per that unit energy. Okay? Does that make sense? So that's the orange curve here. Okay? So the axes are important, right? What we're plotting, and to remember that this density of state is this number per unit energy, and then what we're soon going to see per unit volume. Yeah.
You put density of states on the x if like DOS is like dependent on you.
Yeah, isn't that kind of funny? Because it contains an energy component, so you're like essentially graphing something against itself, like energy versus energy. But it's how did those states change? The number of states per unit energy as a function of that energy.
Yeah, so then why isn't like density of states a function of E? Like why isn't E on the x-axis?
You could totally plot it. Yeah, so what would that look like the other way? I mean, right? I mean, it would look like, if we would just look at this one. There is no damn convention in this field as far as I can tell. We're definitely going to come to a slide here where we look at this. So here, looking at so this is exactly what you were proposing, right? Where we would plot the density of states as a function of energy for a bulk system, and then these more quantum confined systems. Yeah.
So how come on our E versus DOS plot, the one that you just drew on the right,
Yep.
we only see one load because we see the symmetry in the first plot? We're not plotting negative.
Yeah, that's the difference between this and this. Yeah, so we're just plotting this, and we just as easily could plot here if we went if we went this direction, we would bloop. Yeah. So, frankly, the text that chapter 3 is not that hot, and I don't like the organization. So, I guess on the homework, I'll send you some selected web pages or upload something to the text. But just again, my point is that the axes are very important. Okay, and to really think about what this density of state means. Okay. Okay, and we also talked about this relationship, the relationship between the chance of or the frequency with which a state is occupied as a function of temperature and as a function of that state. Okay? So this relationship, we defined E as your energy level of interest, right? And then U as the Fermi level, which is constant until you start doping it or changing other parameters. Then KB is the Boltzmann constant and T is the temperature. Okay? So in the text, they plotted it like this, which makes sense. So we're plotting the frequency, the percent of the chance of being occupied as a function of energy. Okay, so this is plotting right now the next energy above the valence band. So if we have our energy and we have our conduction, no valence, and then our band gap and our conduction. So what is the chance of this being occupied? And so at a positive potential, there's zero chance of that being occupied. And when you start to put in a negative potential at 0 Kelvin, when you put negative potential, you can start to excite an electron. Okay? So it's on-off at 0 K. But as you start to put more energy into it in the form of heat, these bands become, the band gap, what, increases or decreases? Decreases, right? Band gap decreases with temperature. And so it becomes easier to populate one of these conduction bands, right? That's what this is showing. At higher temperature, it's easier to populate a conduction band. Yeah?
Is this just because the extra kinetic energy of a higher temperature means that the electrons can actually move to those upper orbits?
Yeah, I couldn't say it better myself. You have more kinetic energy in the system, yeah.
Doesn't that leave holes in the bottom though? So
Yes.
that doesn't change the band gap?
That's a good question.
Both of them like move up together.
Yeah, so you're saying it does or it does not?
Like the holes get to higher like valence energy.
So he's saying, does this attraction essentially pull the band gap closer together? I don't think it works that way.
Well, that's whenever you excite an electron, you're going to create a hole. So there's
Yep.
always that potential.
There becomes more and more, but that potential is balanced by what you're putting in here, right?
Yeah, because the energy just makes it higher chance for the electrons to go through the conduction band,
Yeah,
and also a higher chance for there to be holes in the band.
yeah, exactly. But I don't think that changes the band gap. Yeah.
Wait, so were you saying that when you increase the temperature, the band gap decreases?
When you increase the temperature, the band gap decreases.
And did you derive that from the graph? Because I was under the assumption that the band gap never changed, like, and it's independent of temperature.
Unless you add extra
No.
dopants.
Yeah.
No, you can definitely add dopants to do that. But so for example, here is blue is silica. So at our regular is 1.17. And here as it changes as a function of temperature, it decreases. And so this is that relationship where you have the regular band gap, and then these are known coefficients of how that changes. Yeah.
It changes like based on temperature, like in relation to a semiconductor is defined as such, like based on regular room temperature, and like as you increase the temperature, like since the ambient energy gets higher, like if you're open larger band gaps, will like technically be semiconductors. So
That was an explanation, not a question, right?
yeah, like,
Yeah, that makes complete sense to me, right? That as you put more energy in the form of heat, more of these conduction bands can become valence bands. And more of these electrons in your valence band have enough energy to populate the conduction band. Yeah.
If the electrons have energy, like we're plotting this by energy, how could we possibly be at 0 Kelvin, or even the closer you got to that, I would think they would just stop.
Yeah, isn't this what this shows then? Right? Is that, well, this isn't showing that it stops, it's showing that it, and again, this is not 0 Kelvin, this is low, yes, this is 25 Kelvin. But that the rigidity of those bands is much more locked in place at lower temperature. Yeah, yeah.
so in a way we could interpret the steepness of the slope on this graph as the band gap.
It's related to it.
Yeah, I mean, so it's like this between the two asymptotes, I guess, would kind of, I don't know. I don't think so though. But it's clearly related to it, but exactly how mathematically, yeah. Okay. So,
I have a question.
yeah.
I'm trying to like make sure that my logic is valid. So, if you're putting more energy into an atom and these electrons are moving, those movements are what accounts for the band gap decreasing. Because
Well, these are no longer atoms, right? This is now an extended solid.
yeah.
So all of their wave functions are completely overlapped, right? Like we have like a chunk of silicon at this point, or a chunk of germanium, or a chunk of a silicon. So that's why you have, you know, so many infinite numbers of energy levels, right?
So basically, we're putting energy, and as long as that energy input is constant, those electrons are moving up, and then because they're moving up and staying up because of that energy flow, that's how we can consider that the band gap is decreasing because of that movement, but it's not really like, it's not in actuality, like, you're not changing the position of the orbitals, it's just because those movements is why the band gap decreases.
Yeah, I mean, the wave functions I don't think are changing, but as you have more energy into the system, you can populate more of those energy levels like we originally drew for hydrogen, right? Yeah. Okay, so that's for conceptual. So actually, let me copy and paste this. We did not solve this problem in class last time, right? We started and then gave up?
Right.
Okay. So, could you do this one? Let's just look at silicon. What are the probabilities of electron promotion at 300 Kelvin into the conduction band for diamond graphite and bulk silicon? And there's the Boltzmann constant with units of electron volts. Okay, so we know KBT, known, and we're solving for probability of electron promotion. So F of E is our question mark. So then we need to know E and Fermi level. So here, E is our E of interest. Electron promotion into the conduction band. So this band right here. The very, very lowest energy level in the conduction band. Okay? It could have said, it could have given you a number, right? It could have said, I know the band gap is 1.17 electron volts. What's the frequency at 3 electron volts? Or 10 electron volts? Or -5 electron volts? Okay? But it didn't. It said the lowest into the conduction band, so right here. So that's why this is tricky, yeah.
So you said, so this says what are the probabilities, but then you just, I think you used the word frequency.
Did I? Yeah, that's
So-
probably bad word choice.
Okay.
Yeah,
So this equation represents the probability? Okay.
yeah, yeah, sorry,
Good question, Paul.
yeah. This is how it's plotted here, right? So you either have, so this is a 50% probability of this being occupied.
Okay.
Yeah.
got it.
I mean, by frequency, like you could also, how often is it occupied? So how often is this occupied? 100% of the time, but not frequency as in like
Hertz.
a hertz. Yeah. So sorry, let's strike that from the record. Okay, so the reason this is kind of tricky is you need to remember the definition of the band gap, right? And so we know that the, why am I getting lost here? That your energy of interest, the very bottom of this is halfway between here. Right? Let's just write this out. So the band gap is 2 times this distance, right? So here, this is our E sub I, and the distance, this is E sub I minus Fermi level, E sub I minus Fermi level.
And is it E sub I that's in the equation?
I mean, this is just written as E, but it's this E right here.
Okay. Which is
Right.
EG above the valence band.
No, not EG above. Oh, yeah, above the valence band. Yep, above the, yeah, EG above the valence band.
Can you repeat that?
He said, so if we draw it, he said this E sub I that we're interested in, right, is EG band gap above the valence band, right? Yep. So the trick here is to recognize that this distance then is this distance is EG over 2, right? And this is band gap over 2. Yep.
So in this case, are we using EF and mu interchangeably?
Yes. This was another disclaimer that I had here, is that when you start looking at other references, that they will use this. Even though your text goes out of its way to describe these as being different, many other resources do not. Yeah.
In this case, EI, are we referring to that as both the bottom of the conduction band and the top of the valence band?
Say that again.
Why are we able to just say that double EI minus mu equals energy to band gap? It's not really clear why we can say that the top difference and the bottom difference between valence and Fermi and conduction and Fermi are equivalent.
It's based on the definition of what the band gap is, and the fact that we're at this lowest energy level. Right? Yeah.
That's because our discussion earlier was that the Fermi level never changes, whereas the band gap does change, because the Fermi level is always in the middle, but as you bring those closer together, right, there's no change.
Still.
So that's why the Fermi level is more of like a standard that we would maybe know usually.
Yes. Let's just write this as EF, right? Let's just assume. Let's say this is EF. Okay. Yeah.
Is there a convention thing going on here? Because EI minus EF for the top section towards the conduction band would be positive, but for the bottom section towards the valence band would be negative. So they would cancel. Or is there?
Oh, I get what you're saying. So if you added like this and this, does it become 0? I think you're taking absolute values here. Yeah.
According to our equation, it's always the positive value because E sub I is the lowest part of the conduction.
Yeah, but this could also ask you, like, what's the probability of at this energy level, right? So in that situation, if you had it to a negative value, it should be a high number, right? So a large chance of being occupied, right?
Yeah, that makes sense. You don't need an absolute value of that.
Yeah.
That exponent will just become very small.
Yeah. And so the chance of this being, as this drops to 0, right? I mean, if this drops to 0, you have a 100% chance of being occupied, right? Okay, so then this would just become 1.2 electron volts divided by 2 over 8.6 times 10 to the negative 5th Kelvin, 300K. Equals 1 over e to the 23 So a very low chance of being occupied. So what do you think, how do you think this number changes for, I mean, this example is right from the book. So how do you think this changes then for graphite?
Yeah.
But they just missed it on the one before that.
Oh, yeah. Right, so what do you think happens with graphite that has no zero EV band gap? How much higher? 0.5, right? So if EG is 0, then now your 0 divided by 2 is 0. E to the 0 is 1. Right? So what about then something like diamond that has a really big band gap? I think you have higher or greater probability. Higher or lower? Lower, right? If this band gap becomes even greater, it takes more and more energy to populate the conduction band. And that chance goes down. Okay? Yeah.
So is this function the probability above the energy value you have of it being occupied by an electron?
Say it again.
So is this function give the probability above a certain energy level of it being occupied by an electron?
My understanding is that it is at each energy level, right? So,
And then like for graphite, Eg equals 0. So then if you measure above it in the conduction band, there's like a half probability of it being in the conduction band, right? So it's measuring above the 0.
Well, it's.
I mean, to me, this is the probability or of being occupied at that point, and only that point. Not above it, not below it.
Yeah, okay, I remember.
Right? Yeah.
Wait, so I guess I'm a little confused because I thought that f of e is the probability that E is occupied, but in the problem we're using f of E as a function of probability of electron motion.
Isn't that the same thing?
Oh yeah, wouldn't it be all the energy levels above the band gap? Because the electron could be,
But like in promotion, you're implying that it's starting out at a certain energy level, and then it's like, I don't know, I guess it's like a wording that I'm confused about. Like it's just that.
I mean, it's not like it here. At this point, I don't think you can think of it as all conduction bands are full. That's not what this is saying, to my understanding. It's the chance of your energy level of interest. How does your energy level of like this or this change as a function of potential? So these could have these different energy levels could have similar. So if this is EV, F of E. Okay, so here, this would be more likely to be occupied if that looks like this. This would be, God, it's going to be lower. Is it going to look like that, or is it going to be shifted? Tell you what, let's look at a situation where they're doped. I've got a sketch for that. Okay, so here's our density of states. This is a, let me just label it here. This is N-type, and this bottom one is P-type. Okay, so here we've added electrons. And on this bottom one, we've added holes. Okay, and then the top one is undoped. So we're shifting it up or down. Okay, so when we add in electrons, we're shifting the probability of being occupied up. When we add in holes, we're shifting the frequency of being occupied down.
So how does that relate to the probability of promotion?
Probability of promotion. I still don't get it. Isn't that the same thing?
But it's not like being promoted, like it is.
I mean, the probability of being promoted then is a function of the energy.
So you can't be like add 300 Kelvin, or you like heat it from 0 to 300 Kelvin, and then you're asking what, like.
It's just probability that an electron exists there. They aren't really promoted there because it's just a big.
It's a giant wave function, right?
Yeah, I guess I was confused about like the probability of promotion.
I would think of it as probability of being occupied, of that state being occupied. Yeah, yeah.
So could we say that in N-type we'd be much more likely to find electrons in the conduction band?
Mm-hmm. Yeah.
So for like these N-types, P-type, P-doped semiconductors, are we gonna, is the Fermi level the same as the Fermi energy here, or would there be
Let me see what I have there. Okay. So P-type, where we've added holes, N-type, where we've added electrons. Okay. So here, the ED, this is the energy of just, the way I understand it is this is the donor, right? Which is different than the band gap of your material, right? So this makes sense that the energy of your donor is higher than of your acceptor, right? So now this pushes the Fermi level up, and that pulls the Fermi level down in terms just by adding them. Does that make sense?
So
because it's no longer a different, it's a different material.
Yeah,
right?
So is the Fermi energy still right in between half, or is it the same thing with mu?
To me, then the Fermi energy would be right there.
Okay, so that stays constant.
Yeah. Yes. Okay. Another way that you see this expressed that I just wanted to walk through, because you guys asked me a question the first day that I didn't have a solid answer for. Well, I thought I had it here. Is that sometimes we also saw drawn like this, right? And you, for example, I threw up that example of like a metal versus a conductor, where a metal looked like this, and then an insulator or a semiconductor looked like this. Right? Remember that? I forget who asked. What they're plotting there now is this carrier concentration, and its density of states times the Fermi distribution equals this. Okay? So let's walk through it. So in the center, it's easy. There's no states there, so you're multiplying by 0. Okay? At least for this is, let's call it a semiconductor. Say this is less than 4 electron volts. So no chance of anything being there times it's kind of a weird thought experiment that there's a probability that it could be there, but there is no state for it to exist in, okay, equals 0. Here you have the other thing that's confusing about this is that now this is flipped. So here our probability is on the x-axis. Follow? Okay? Energy is on the y-axis on all of these. Okay? So here we have a lot of states, but not a lot of probability. Okay? And that's why we get a situation like this. Now, what's confusing is when I got down here and I was like, okay, so this is 1, and this is also high, so why doesn't this like go out indefinitely? But the reason is because now you're plotting the inverse because you're looking at holes. So this would look like that. Right? So below this point, you would start to use the negative probability distribution because you're looking at holes. Okay?
Is that
Below 0.5, I would think. Right? Or exactly, 1 minus the probability is exactly what it is too. Yep. Yeah. Yeah, so you could think of this as like drawing two different curves, like the inverse curve. Like what's the whole probability?
The bottom is the inverse curve, the top is the...
Exactly. Yeah.
So below the Fermi energy, we use the inverse of Fermi-Dirac.
Yes. So going back to what made me feel so inadequate at first was when I saw that the number 1 density of states figure had nothing to do with my density of states lecture. Now I feel comfortable that my understanding matches the cumulative experience of the internet, right? That we now understand these density of states, understand Fermi distribution, and understand their product, this cumulative distribution of electrons and holes. Okay? Yes?
So since Fermi level depends on temperature, can we change the n-type and p-type semiconductor by just changing temperature?
Can we change the what?
N-type and p-types of semiconductors?
Yeah, absolutely. Yeah, so just like we can, so those are the most common tools that you can use to modulate a semiconductor, temperature and the doping. Yep. Yep.
Can you think of there as being like 2 Fermi distributions? Like there's
Yes.
one for electrons and then one
Absolutely. That's what he was just saying, the inverse. Yeah. Yep. Okay. I was going to try to start to derive this equation. There's an equation, there are equations for how do you calculate the density of states. Because this is actually a number, right? Like you can actually calculate. This is not just theoretical. You can do the math to calculate. If I have 1 cubic centimeter of silicon at 300 K, how many density of states are there? And so maybe we can just start to think about a few things. That what the density of states is in a semiconductor is the density per unit volume and energy. Okay? We've defined it previously as just energy, but we can also think of it as per volume, right? Because now when we were thinking about it like here, so this makes sense, the number of states per energy. But what if I have a small piece of semiconductor, a big piece of semiconductor? There actually you'll have more states in a bigger piece because there are more delocalized wave functions that have been distributed over that piece of material, right? So what we're going to do next time is think about K-space. And so if you haven't, when's the last time you guys have seen that? K-space and like frequency, the frequency domain instead of the spatial domain? Okay, good. We're all on the same page then. So we'll do a truncated version of the derivation for the density of states. Take a minute and watch a 5-minute YouTube video about k space because what you're looking at is the frequency frequency as a function of 3 dimensions. Okay, how does frequency of your wave function change in x, y, and z? That's why quantum dots are quantum dots, is because you start to lose these dimensions, right? And a bulk semiconductor, you can have this frequency in all these different dimensions. So we'll hit this on Friday.